Good afternoon. I'm Martina Morris. I'm a sociologist and statistician from the University of Washington in Seattle. And my talk today is on modeling networks and epidemics, and in particular, taking a principled integrated approach to building a framework for statistical epidemic modeling. Just a bit of orientation because I think people come from many different disciplines here. My talk's going to focus on mechanistic models for epidemic simulation that differs from statistical estimation of epidemic summary parameters from surveillance data. But the epidemic model that I'm going to talk about has a statistical model at its core. And in that sense, it also differs from the traditional epidemic modeling approach. Here, the statistical model is going to drive the transmission network and ground it in empirical data. So the word model here, I think means a lot of different things to different people. And even in this talk, it's going to mean different things in different contexts. Just briefly as an outline, I'm going to say just a bit about the components of a mechanistic epidemic simulation model so I can highlight the component that I'm going to be focusing on in the talk. The core of the talk is really about how you model social structure and epidemic dynamics with an example of the kind of integrated statistical framework that I think is useful in this setting. And I'm going to end the talk with what I think are some research needs. So I don't have to tell this audience much about the components of epidemic models, but for mechanistic epidemic modeling, there are a lot of moving parts, obviously. There's the demography if you have an open population. There's the transmission network itself, which is contacts between nodes or partnerships if these contacts are durable and repeated. There's the behavior within contacts or partnerships that influences transmission. There's the biology of the pathogen, its natural history and lifespan. There's the biomedical progression within hosts. And then finally, there's the overall public health infrastructure. So lots of moving parts in these models. I'm really only going to focus today on modeling the transmission network, but the approach that we have developed here really fits into this larger mechanistic modeling scheme. The transmission network, obviously in an epidemic, is foundational. It is the way in which a pathogen moves from one host to another. And it's really for the kinds of things that we're interested in here, I think in this workshop, a dynamic social network. Our ability to model this has really improved dramatically over the past couple of decades. And you might be asking yourself, what level of detail do I actually need to represent a transmission network? And the answer to that really depends on the properties of the pathogen and the purpose of the model. So pathogen properties that influence what level of detail is necessary really are about how easy it is for the pathogen to spread. If it spreads very easily, then the kind of structure in a network will probably be overwhelmed very quickly. It might matter in the very beginning, but not so much at the end. Whereas if a pathogen is harder to transmit and requires a kind of contact that is fairly unusual, then the structure really comes to the foreground, the network structure, because the network structure then is essentially what allows for connectivity in an otherwise sparse regime. But the other thing that really matters is the purpose of the model. If you're simply interested in getting a summary indicator, like the reproductive rate, then it may not require as much detail. Whereas if you really want to drill down into specific population level disparities, then clearly more detail is needed. The length of the projection period, whether or not you want to assess interventions, and finally, whether you're interested in informing local epidemic response planning. All of these things determine the level of detail that you're going to need in a model. So there are multiple levels of network structure. At the macro level, you might be talking about pandemic transmission around the globe. At the meso level, you may be talking about transmission in a larger community where it's structured by things like social contexts, hospitals, workplaces, schools, etc. Or you may be interested in a smaller setting where you're really representing at the micro level the actual interactions between each node and each other node. the level of the model that you are using really determines both the structure that you're going to employ and then, of course, the data requirements. Macro level models typically take the form of a bipartite network. This involves what we call two modes, people and countries, or some other larger unit. We're frequently interested in heterogeneities in both the people and the places. Example of this would be travel restrictions. You might ask the question, how effective are they for reducing pandemic spread? It's an open question, obviously. At the meso level, we are also interested typically in bipartite representations. We have now multiple settings, and you've got persons as one mode and settings as the other. There are, again, heterogeneity in attributes for both of the modes, persons and settings, and often heterogeneity in the ties as well. So there will be setting-specific patterns of ties. The duration may be fixed or may not be, but it's often fixed, as well as the intensity. An example of this would be asking the question, how effective is it to close schools in the context of an epidemic? Here you might expect a bipartite representation with a two-mode network where you have persons. Note that there are multiple settings. So there are households, workplaces, schools, other settings where people congregate. And I'm going to show you an example that compared 152 countries on this next. There are heterogeneity in all sorts of attributes here, but the heterogeneity that I'm going to show you in this example really focuses on age and the age composition of households and how that varies across countries. And then there are heterogeneities in ties. So really what is going to be of interest in this particular setting is how the age mixing changes by setting and how there is overall variation by country in those settings. So the example is a polymod-based study of influenza-like transmission, where the data that they collected are sample survey data with a 24-hour contact diary. And because they're comparing to two other surveys, they're doing lots of intermediate modeling. When I say two other surveys, they are surveys that involve global surveys of demographic and health statistics, so they occur in many different countries. They focused on the heterogeneity in age mixing, and what they wanted to represent was both how that varies by social context, i.e. by where the contact is taking place. It can be in the home, in the workplace, in schools, or in other settings where people congregate. And what they've represented here, it will be familiar to people who have worked on mixing matrices before. It's the age of a person and the age of their contact. So in that grid, you're seeing the age mixing pattern for dyads. And you can see that that pattern varies dramatically by the different social contexts. So it tends to be fairly high on the diagonal, but also subdiagonals for the household. It's kind of this square random mixing pattern within workplaces. There's also an interesting pattern in schools and in other social settings. It also tends to be fairly assortative, and you can put all of these together and then see what the age matching pattern looks like. But there is also variation across country in these patterns. So the three different columns here represent 3 of the 152 countries that they looked at: Germany, Bolivia, and South Africa. The bottom line is that they found that the heterogeneity that they're observing in these patterns that generates different forms of age mixing in the population leads to very different implications than for intervention impacts. The effectiveness of school closures in particular and workplace contact reductions varied dramatically by country. So there was no one size fits all, and the structure really made a difference. At the micro level, we're typically talking about a single setting or representing a single population and all of the interactions between nodes in that setting. We're interested again in nodal heterogeneity, in tie heterogeneity in terms of the type, the duration, and intensity. And here we often focus on something that we call dyad dependence, that is dependence in the partnerships or contacts between dyads in the timing and sequencing of these events. So an example of a question you might ask here would be, can work scheduling reduce hospital-acquired infection rates? And I'm going to show you another example here that of a study that tried to take a look at this using a network lens. So again, we're interested in nodal heterogeneity. Here we're looking at the roles of nodes: patient, nurse, doctor, administrator. We're looking at tie heterogeneity, the duration per encounter, and the frequency per week. And the dyad dependence comes in terms of the temporal sequencing of these links between people in each of the groups and the way that scheduling constraints influence these. So this study was a study of a single ward in a hospital, a facility, and they had everyone in the facility spend a week wearing these proximity sensors, and they could then categorize from the stream data all of the interactions that they observed and break them down by the groups that were having interactions in terms of the frequency and the intensity of these interactions. And essentially what they found was the rescheduling that they tried, which was rewiring the network essentially to reflect different scheduling constraints, ended up they could find a version of that that worked as well as isolation in reducing hospital-acquired infections. And the reason that's important is because isolation is actually not a good strategy for dealing with a sick individual, because they actually need to have contact. So it was a nice way of showing that if you rewire the network, you can achieve some efficiency in hospital-acquired infection reduction. So just to think a little bit about the data implications of an approach like this, it's worth understanding how data is integrated into the workflow. So in a lot of mathematical modeling, the mechanistic modeling for epidemics, data is treated as input parameters. This is often culled from the literature as opposed to primary data collection. And you can often get something that looks like a Franken model where the data are really coming from lots of different places, not a single population. This can still be useful for what if type studies, but it's different than an approach that starts with data as really foundational, in which case you develop an integrated statistical epidemic modeling framework for representing the spread of infection in a population of interest, and you're interested in that specific population. This is really the best platform for policy support. There's also a difference between big data and little data. And while I think a lot of people are very interested in the huge passive streams of big data that are now available, I think there's still a large role that can be played by active, efficient sampling, the little data. So I'm going to give you an example of one of these integrated frameworks for statistical epidemic modeling that started with a question in our lab about 25 years ago, which was, why are there such large variations in HIV prevalence at every scale? And the work here really began with some qualitative social research, some ethnography, in Uganda back in the 1980s, where the local communities had really identified the possible role of what came to be called concurrent partnerships. That is, people having more than one sexual partner in an overlapping interval. So the intervals of the partnerships overlapped, and you're going back and forth between the partners. It's not just multiple partners. It's having them at the same time. That generated a public health response in the late 1980s in Uganda called the Zero Grazing Campaign. And that in turn resulted in an 80% reduction in HIV prevalence over the subsequent decades. So it was a pretty remarkable sequence of events. And that's what led us to be interested in trying to understand the role that concurrency might play. So as we dug down into thinking about this, the reason concurrency is interesting is everybody understands that multiple partnerships, the more partners you have, the more road surface there is for the transmission, obviously. But this wasn't about having lots of partners. You might have a few partners, but because the partnership intervals overlap. So it's a subtle sort of timing and sequencing question that plays right into the kind of dyadic dependence that the micro modeling for networks is good at capturing. So the way concurrency works is it really removes the protection of sequence over time. Under serial monogamy, in this case here, you get to be partner number one, partner number two, or partner number three of this central node. And chances are, if there's an infectious disease running around, you'd probably prefer to be partner 1 rather than 2 or 3, because it makes for less chance that the central node has already become infected. But the sequencing of partnerships here gives you that protection if you're partner number 1. With concurrency, if you're partner number 1, you may still be partnered to this node when they start an additional partnership with node 2 or node 3. So what that creates is this new backwards path. Your sequence, the fact that you got there first, does not protect you. It's a whole new chain of infection, not only to you, but then obviously to any other person that you have contact with after that. It also amplifies the spread, the forward path of infection. It increases the velocity of that because you don't have to wait for a partnership to end before the next one begins. And it ends up generating a unique cross-sectional network signature. Under monogamy, if you look at a network, the largest component you can observe is of size 2 by definition, because that's what monogamy means. You only have one partner at a time. But under concurrency, if I have more than one partner, my partner might have more than one partner, and you might get this long, loosely connected web, even in the cross section. So it creates connectivity. What we found that was really interesting was that this connectivity has a threshold property, and that threshold property is really what we see in epidemics as well. So imagine that you have a toy network here. You've got 10,000 nodes, and the distribution of the number of partnerships that people have at that moment in time is given by this histogram. You can have a maximum of 3 partners at a time. A small fraction, maybe 10% of the population has that. The other 90% of the population is split between having 1 partner or 2 partners, and the mean is 1.68. The largest components that you get if you simulate from a network distribution, degree distribution like this, are on the order of 2% of the population in the largest component, and the components themselves look like this. If you increase the mean number of partners by just a bit, this is 0.06 of a partner, so 6/100ths of a partner, and just a small increase basically in the relative fraction of people having 2 partnerships. You start to generate larger components in the network. The largest component on average has about 10% of the population now, and you begin to see the development of something we call a bicomponent, this red ring here. It's called a bicomponent because you have to remove 2 nodes or 2 links in order to disconnect it, really. It doesn't sound like much, but think of it as doubling your intervention effort to get the same effect. If you increase by another 0.06 of a partner, you now have 41% of the population connected and 5% of the bicomponents and another 0.06. And now you're up to 64% of the population connected and 15% in the bicomponents. This whole change here from 2% of the population connected to 64% of the population connected occurs with maybe 15% of people changing behavior and a change in the mean of 0.2 of a partner. So the moral was essentially a small change in behavior can make a really big difference in the connectivity of the network. And it's bad news when you're moving from left to right, but it's actually good news moving from right to left, because it means that your intervention effort doesn't have to change everybody's behavior, maybe only 15%, and you get back from 64% connected to 2%. So obviously, this cross-sectional connectivity does interact with temporal connectivity. And you can think of epidemic persistence as a function of both the static and the temporal connectivity in the network. The static connectivity is the density. It's the partners per capita on any day in the network on a cross-section. The temporal refers to the turnover. It's the partners per capita, say, over the lifetime. And you can do formal analysis to look at how the emergence of a giant component, there's a threshold for that basically, and what the contours of that look like as a function of the cross-sectional density and the temporal turnover. So basically what we are doing here in this diagram is showing you those contours where you compare 2 different versions of cross-sectional connectivity, one allowing for concurrency and the other enforcing serial monogamy. And what you see is that there are some regions here where you're going to get epidemic persistence for both monogamy and concurrency. And that's because either the density is high enough or the turnover is high enough that the epidemic can persist. You also have some areas here where you're going to get eradication for both density and turnover are low enough. But then you have this really interesting area in between where you get persistence of the epidemic only with concurrency. So the threshold for the giant component for concurrency for the same values of density and turnover is much lower than it is for monogamy. Basically, there's a region where epidemics persist only with concurrency, and that led us to think about, oh, so maybe that's what's going on. We can see that it doesn't take large differences in behavior to generate large differences in connectivity. So maybe that's what's generating. It's this, we're sort of in this area basically, and that's what's generating the difference in HIV prevalence in these different settings. So how do you model all of that? So the framework that we developed has been it's called the temporal exponential family random graph model. It's a temporal cousin of the ERGM, which we also developed over the last 20 years. ERGMs are generalized linear models for dependent data. It's a statistical model basically for pair formation and dissolution over time, where the probabilities of formation and dissolution depend on the properties of nodes and the state of other links. So these are the dyadic dependent terms. What's unique about this framework is that the model is used both for statistical estimation from data and also then simulation. It's the heart of the epidemic model, the mechanistic model as well. So it's a bridge between the empirical data and the epidemic model. The general form of an ERGM, I'm just going to show you, I'm not going to spend a lot of time on it. It's a stochastic model that describes the probability of a graph Y. Little y here as a realization in the sample space of all networks of this size, which is a function of theta prime and g of y. So g of y is these vectors of network statistics, and those are essentially counts of different kinds of configurations of nodes and links that make your network more or less likely in the space of all possible networks as a function of what the model parameters, the estimated model parameters say is the impact of that statistic. Is it more likely or less likely than you would expect by chance? And k of theta here ends up being a normalizing constant, which is the numerator summed over all possible networks on a node set. That's a lot of networks, so of course this ends up being a computationally intensive approach to both estimation and simulation. These G of Y terms make this an interesting approach to trying to understand how to represent a network. So what can you represent with a network statistic? Well, you can represent heterogeneities in this cross-sectional degree distribution, that's our concurrency term, by one or more nodal attributes. So there can be heterogeneities in degree by things like age and sex. You can represent that in terms of a difference in the mean degrees by age or distributions. The entire distribution can be represented parametrically or non-parametrically. You can represent mixing by nodal attributes. Again, mixing by age would be a classic example. It can be assortative, disassortative, or bespoke. It's fully general in that sense. You can have non-parametric versions of this for discrete term attributes and parametric versions for continuous variables. You can also represent higher order configurations. Examples would be a triad of different types or cycles of various sorts. And all of these terms then can be used in both the formation and the dissolution model to capture both the cross-sectional and the temporal structures that generate connectivity in your particular network. It's a fully general modeling framework, and all of the terms are jointly estimated. And because this is a statistical framework, you have a lot of additional benefits that come along for the ride. It allows for, because it's so general, much more complex structure is now accessible to you than other forms of agent-based modeling. You have both traditional and novel network-specific methods for model assessment. You have scaling assumptions that can be used to handle open populations, so that allows for changing size and composition of the node set. You can use multi-layer network models with cross-network dependence. The dissolution model can be adjusted for competing risks like mortality in an epidemic model. And the models can be estimated on some forms of sampled network data, and that's particularly important. So if we think about what data are needed for estimation for these kinds of network models, it's basically data on the sufficient statistics of the model, the G of Y terms. Now, you're always going to be able to observe these on a complete network. You just have to construct them. But for some statistics, you can also observe this G of Y from a sampled network. And this really opens the door to principled inference using small data, which is nice because it makes it feasible. The most efficient, most compact, and most common design used in the literature is called egocentrically sampled data. This is a sample survey of respondents, the way you would do a normal sample survey. We call them egos. We ask the egos to report on the attributes of their partners and the age of their active partnerships. If you have a probability sample of egos, you then can support principled inference to the network in the population of interest. So altogether, this becomes then a principled integrated modeling framework for data estimation and epidemic simulation, where you can use really small data, a single cross-sectional egocentric sample of, say, 2,000 nodes, which can be used to estimate the parameters of a reasonably complex tergum, and then use that tergum to simulate an epidemic across that network for a dynamic, complete network of arbitrary size in an open population, which you can guarantee will reproduce the appropriately scaled network statistics, your G of Y terms, in expectation. How computationally intensive is this? Well, it's intensive, but it really depends a lot on the model and the size of the network. The practical limitations here have changed dramatically over the last few years. 20 years ago, we would be able to estimate these dyadic dependent models on a 1,000 node network, and maybe it would take hours or days to estimate on a laptop. But now, a 50,000 node network with the same model takes about 3 minutes. Simulation on 1 million nodes is also very quick. And we've had really major improvements in algorithmic efficiency, not computing power. It's not computing power that's really generating these. Part of it is that when we exploit the scaling principles using these size and variant parameterizations, it means that if we want to simulate on 1 million nodes, we can do our estimation on a couple thousand nodes, as long as the appropriate statistics are reliably estimated in that size. And the other thing that's really changed is the algorithmic improvements. And we use a range of different algorithms, simulated annealing for the egocentric designs, maximum pseudo likelihood estimates to get the estimation started. But the real engine behind all of it is an MCMC algorithm. And we've had massive improvements in efficiency in all of those areas. So given that, what would I suggest is needed now? What do I think is needed now for pandemic preparedness? And I would say the key lens I would adopt is to prepare, you really can't be caught kind of on your heels. You need to have the tools ready to be able to move quickly. And that is a combination of both your models and the data. So the models, I would say, the statistically integrated epidemic models are very useful for policy response modeling. And what we really need that we don't have is a strong framework for the bipartite network modeling. These are really the models that we need for the contact-free pathogen epidemics, airborne and fomite transmission. We don't have the same understanding that we've developed in these micro models for the key bipartite statistics that we need to represent effectively the structure of a bipartite network that matters. And once we do, that will derive then some implications for data collection. I think the other thing that we need is methods for estimating models from link-traced network data. We have generated a huge amount of contact tracing data over the last year in COVID. And as we faced 20 years ago with the world of HIV and contact tracing, we don't know how to model population level impacts from those kinds of link traced data. It's a long-standing fundamental statistical issue. There are, I think, some tools that can be used in the adaptive sampling universe, and lots of recent work on data augmentation, but that really needs to be developed. On the data side, I think we need to be thinking about doing routine surveillance with active sampling and passive stream designs. We really want routine collection of population level sample data. I think the Polymod study is a good example of that, that we can rely on when the crunch hits. If you're designing your study and trying to collect the data once the disease is there, you're too late. So we need to be doing this on a regular basis, and it is possible. On the passive streams of big data, I think we really need to classify the streams that are relevant to specific population pathogen models, recognizing that the streams that you have available can inform some kinds of models and not others. So getting that classification and understanding how to use those data effectively would be useful. Finally, on the computing side, I would say we need more designs for algorithmic efficiency. And my sense is that the big gains are going to come now from bespoke algorithms that are designed specifically for the population and transmission networks of interest. Over the last couple of months, we've experienced, after 20 years of working with these algorithms, another 4 to 6 fold order of magnitude reduction in computing time, largely by developing some bespoke algorithms. So with that, I'd like to acknowledge the members of the large team of people who've been working on this over the last 25 years, the StatNet development team, the Epimodel Research Lab, and the Network Modeling Group at the University of Washington. I'd particularly like to thank NICHD funding for consistent support of model and software development, which is not easy to find these days, and a couple of the centers at the University of Washington for supporting this research. In what follows, I'm just going to be showing you some screens with resources. I'm not going to talk them through much. They're just there for you to go back and take a look at. We do have some Shiny apps online so that you can kind of play with and get a feel for how these tools work. And we teach a workshop on network modeling for epidemics every year. That's a 5-day intensive training course in August. The StatNet software and methods have a huge literature at this point. Just a heads up that the original paper or papers, it was a whole volume, 8 papers on ergoms and StatNet that came out in 2008. We have a major update, ergom 4.0, in preparation, and a JOS paper that will probably come out later this year. Epimodel software. So Epimodel is the software that sits on top of StatNet that does all the rest of the mechanistic modeling. And that now has a fairly large literature as well. There's literature on concurrent partnerships and the role that they play. And I would like to thank you for your attention. Thank you.